This video, we're going to look at an R program. It's going to read some data from an Excel file that's on the web, and that data is going to correspond to a charging capacitor. And then we're going to use the NLS method, the nonlinear least squares method, to fit it to a form and then plot both the data and the fit function and with its parameters found by the NLS method. All right, so here we go. So I'm using the openxlsx method. I have used another library for like the read.xl library. This one seemed to work better for reading an Excel file off of the web. So if you don't have it, you've got to bring the library in. And if you don't have that library, it will prompt you to install. For me, it was up here at this sort of top gray area. So I'm reading the data in, and I'm specifying the sheet. And so here's the URL for that file. Here, there was multiple sheets. So this was sheet 2. The first sheet, I think, was discharging capacitor. I wanted the charging capacitor, so I specified the sheet. And this creates a data frame. I think the other library made a list that I could convert to a data frame. This library made it a data frame from the start. And I wanted to rename that the Excel file had long descriptors and units in the headers, which became the sort of the names of the file, the names of the fields. I wanted to rename my fields to simpler names. So I did that next. And so now it's just time and voltage, simple without the units and so on. Now I'm plotting it. I'm using the y tilde x approach here. You can do an x comma y approach, but I'm doing it with the tilde, so I'm doing y first, so the voltages will be on the y axis, that time's on the x axis. It'll have a title, charging capacitor, a label on the x axis, time in seconds, and on the y axis, voltage in V. So I'm putting the units back in on my disk. So there is what a charging capacitor looks like. The voltage across the capacitor increasing with time, but saturating to some fixed value. Okay. Now the formula for this is some number out front, some coefficient, and this is the voltage that it will end up at a very long time. So probably the voltage that you applied to the capacitor. So there's a saturation voltage in here. I just called it A times the quantity 1 minus an exponential of some time divided by a time constant. So this time written out is a variable, and this t is a parameter. So these times will change. This time will, for this given set of data, will be fixed, or we want to find the best one. Same thing for this A. And so we're using this NLS method, and I'm saying that the voltages, so I have this data and I've named it voltage. And down here, in the second argument of this thing, I'm saying that I'm dealing with the charging underscore cap data frame. That's what I called my data frame. So I specify in the second argument the data, and then up here I'm using the y on the data was called voltage. So that's why this is voltage, because it matches one of the data fields of my data frame. A is the saturation voltage parameter. 1 minus the exponential is the functional that I'm then fitting to. Time is the other named data field in my data frame. And then t is my second parameter, the time constant. And so this is the formula, but specifically my y and my x match the names given in my data frame. And then the other things are either functions known by r, like exponential, or parameters I'm going to fit with. And then the third argument here is a vector to give my parameters sort of a starting point. So I'm saying for a start, C is just indicating that it's a vector. And I have a vector, my starting point is a vector of two things. I'm starting off the A at 5. So I say it's going up to 5. It's actually going up to more than 5. And then it's going to take about, I don't know, 15 seconds to do that. So this time constant corresponds to, I don't know, the time to get to like 63%. So it's probably bigger, going to be in the 20s, but this is just a starting point. You've got to give, in the NLS method, you have to give it a starting point. And it should be a decent starting point, or it may fail to converge. Then I'm going to give a summary to see what this NLS method did for me. So that's down here in the console, and we can see that it's telling me that A is about 6, and the time constant T is about 26.7, and seems to have converged. Number of iterations, 2 convergence, 4, so it didn't go to too many iterations because I gave it a pretty decent starting spot. And okay, so now what's next? Now I want to get, I mean, I can just read it off of here, but I wanted to do better than that. I wanted to get from my fit, I wanted to get this 5.998 and this 26.69. And so they belonged to my fit. It had this fit thing over here, has all sorts of bizarro things, because it's a whole process of things. But one of them was this M, and then M had a method associated with it to get the parameters. I'm presuming that's what that means. And then when I got the parameters, that was a list where the things were, or an array where the things were named. So kind of why can't I think of the right word? The arrays where it's named. So I got the named parameter A from the params, and associative array, that's what I'm trying to think of. So sort of an associative array with A, an associative array with T. So that is extracting from the whole fit the 2 numbers I'm interested in. So here we are now, the 26.7 and the 6 I got extracted from the whole fit. So there's lots of data from the fit, but I just wanted the fit parameters. Here's how I extracted the fit parameters. They were part of M. Then I used the get params method, produced for me a list, an array, and then I named my 2 quantities to get the specific values. Okay. Now I want to add this mathematical function to my data. So I'm going to use curve. I'm using vstat. That's what I called the A parameter, and time constant, that's what I call the T parameter. So I gave them just different names, but here we go. So I'm making a curve of vstat times 1 minus the exponential of minus. Curve seems to like the variable to be called x, so I called it x. So vstat times parentheses 1 minus exponential, open parentheses for the exponential, minus x divided by the time constant, close the exponential, close the 1 minus the exponential. I'm going from 0 to 60. That's about my time range. I'm going to make it red. I'm going to add it to what I already have. So I'm not making new graph. I'm adding to my previous graph. And this is the line width. So it's going to be sort of a thickish red line. There we go. All right, I want to display, I'm going to make a little bit more room here. Okay, I want to make a equation to be displayed. So I'm just writing out my expression with these numbers pasted in. So I'm using paste, which sort of concatenates together a bunch of strings. So I'm saying v of t equals, and then I'm using that v number, and I'm rounding it to 3 decimal places. And then I'm multiplying that. I'm using a square bracket here, but this is just a display. R doesn't use the square brackets in this way, but I'm using it just as a display thing. 1 minus the exponential of minus t divided by, and here's the time constant rounded to 3 decimal places. And so that's just creates the displayed equation. And then if I actually want to display the display equation, then I use text, which is going to add it to my plot, and I tell it an X and a Y and what I want it to add. So I'm adding it at an X position, and this is going to be sort of roughly the center. So 35 is about here, Y of 2 is about down here, so I'm going to put it in sort of this vicinity down here and run that. And there is my fit equation displayed. Okay, that's what I wanted to play around with. 2 things. I've used a different Excel accessing library than one I've used in the past. It was better for working with the web. It was also directly gave me a data frame, so I think it's kind of nicer than what I used before. And then also new for me is this NLS. So this was a function that couldn't simply write in sort of a linear form. Like if it were the exponent, the discharging capacitor is just a pure exponential, and I could work with a linear model and play some tricks. But this form required me, if I didn't want to play too many tricks, if it forced me to use the NLS, put in the form, put in the data, put in a starting place, and then how to extract these parameters from that fit. So that was the game. That's what I wanted to show you. Thanks for your attention.